Myself Sreevani, working as an assistant professor in the Department of ECE in Institute of Aeronautical Engineering. So in the today's lecture, we are going to learn the topics or electric potential, then how it is related with electric field intensity, then resultant will be yields. There is a relation between the two terms called electric field intensity E and the electric potential as V. Then followed by we are also going to learn energy density in electrostatic fields. So now the first one which we are going to learn is here the relationship between electric field intensity E and the electric potential V as describes. So yields us here the second Maxwell's equation to be derived for the electrostatic fields. Hence, the relation between the E and V resultant equation is said to be Maxwell's equation for the electrostatic fields. So, before going to derive the relationship between electric field intensity E and the electric potential as V, and we know that we have discussed electric potential V can be defined as here work done per unit charge, and it is given as integral L E dot dl. So in any closed surface, there must be, they won't, here it won't exist, electric field won't exist. Hence, in any, if you consider any closed path, then inside the closed path E equal to 0. Now according to that, if V equal to 0, then integral L E dot dl becomes 0, hence potential becomes 0. So this is the way we have learned the definition for electric potential V for a point charges and three continuous charge distributions we have discussed in the previous lecture. So for a point charge case, this electric potential V can be given by Q by 4 pi epsilon naught into R. Suppose if you want to find the distance from two reference ends, then this electric potential or scalar potential, this V can be given by here Q by 4 pi epsilon naught into R minus R dash. So if you have only one point charge means we know that the electric potential can be given by V equal to Q by 4 pi epsilon naught into modulus of R minus R dash. So instead of having a single point charge Q, then we have n number of points and we want to locate all n number of point charges with respect to the respective positional vectors, then V can be given by Q1 by 4 pi epsilon naught, then modulus of R minus R1 plus Q2 by 4 pi epsilon naught, modulus of R minus R2 plus and so on if you continue with the n number of charges Qn by 4 pi epsilon naught into modulus of R minus R k. Right? So if you approximate this equation, then Q means here 1 by 4 pi epsilon naught as common, then summation of these two can be written as Qk by modulus of R minus Rk. N numbers means where k equal to ranging from 1 to n. Suppose if you substitute k by 1, then Q1 by R minus R1 like that. So if you continue it for n number of variables, then the electric potential V can be given by this final equation. So from this, we are going to derive the electric relation between electric field intensity E and the electric potential as V. Now the potential difference between the points A and B are the two reference points and it is independent of the path taken. Means suppose consider here the figure conservative nature of an electrostatic field. So in that if you consider two reference points as A and B, now if you observe the directions from A to B moving and B to A moving directions, A to B moving direction will be like this and B to A direction will be like this. Hence it becomes completely one closed path. So if you apply electric field to that, then it can be given by here. If you observe the directions from A to B and B to A, and these two are given by here VBA equal to minus of VAB. Right? So now if you add these two, means if you observe the directions of A to B and B to A, two are moving in opposite directions. Hence, the potential from B to A will be opposite to that of A to B. Now from that we have written VBA equal to minus VAB. Similarly, if we add those two, the path means A and B path will be independent of the path taken. Hence, VBA plus VAB equal to integral L E dot dl. If we close that line, then it becomes a surface. Then closed integral L E dot dl is equal to 0. Now, VBA equal to minus VAB. Hence, if we substitute in place of VAB by minus VAB. So, VBA equal to minus VAB. Now, by adding these two means VBA plus VAB, which is equal to, if you substitute VBA by minus VAB, then minus VAB plus VAB gets cancelled, becomes 0. Hence, closed line integral L E dot dl is equal to 0, and consider this as the equation number 1. Now, by applying Stokes' theorem to that equation number 1, as we know that Stokes' theorem gives the relationship between line to surface integrals, and it is given by, according to Stokes, the theorem is given by closed line integral L A dot dl is equal to integral S del cross A dot ds. So, as we know that the Stokes theorem gives the relationship between the line to surface integrals, and here line integral term means closed line integral A dot dl is equal to integral S del cross A dot ds. So, where del cross A is denoted with the curl of any vector field. So, here A is said to be a vector, and in place of A, here we have a vector field term called electric field intensity E. Hence, closed line integral L E dot dl is equal to integral S del cross E dot ds. So, where electric field intensity E is a vector. Hence, if you apply Stokes' theorem to that equation number 1, then it becomes closed line integral L E dot dl is equal to integral S del cross E dot ds. So, from equation number 1, LHS part of this becomes 0. So, if LHS part of equation number 1 tends to 0 means RHS part of that also becomes 0. So, now integration and differentiation gets cancelled. Then from that we have written here del cross E equal to 0. E is always a vector, right? So, del cross E bar equal to 0. So, from this statement we can say that curl of any vector field is equal to 0. So, this is called the point form or differential form of the Maxwell's equation to be derived, right? So, integral form also we know that is integral L E dot dl is equal to 0. So, here closed line integral L E dot dl is equal to 0, or del cross E bar equal to 0. So, this is said to be closed line integral L E dot dl is equal to 0 is said to be integral form of second Maxwell's equation to be derived from the relation between electric field intensity E and the electric potential V. Now, del cross E equal to 0 is said to be point form or differential form of the second Maxwell's equation to be derived for the electrostatic fields. Now, in order to get the relation between A and V, we have to consider here a term called conservative vector. So, what do you mean by conservative nature of any vector? Means the vectors whose line integral does not depend on the path of the integration are known as conservative vectors, right? So, its line integral does not depend on the path of the integration, means that is independent of the path taken. Hence, these vectors are said to be conservative vectors. Now, we know that the relation between here is given by V equal to minus integral L E dot dl. Now, if you consider both sides differentiation, then V becomes dV, and here integration differentiation gets cancelled, E dot dl is left out. So, this E dot dl can be expressed in terms of Cartesian coordinate system. Hence, it can be given as Ex dx minus Ey dy minus Ez dz, where Ex, Ey and Ez are given by magnitudes of the respective directions called x, y, z directions. And dx, dy, dz are the differential components in x, y, z directions. We consider the coordinate system as here rectangular type coordinate system. Right? So now the equation for dv is obtained as here minus ex dx minus ey dy minus ez dz. Now if you consider here the normal differential component of the electric potential dv, which is expressed in the vector forms. Vector analysis is given by the formula as dou v by dou x into dx plus dou v by dou y into dy plus dou v by dou z into dz. Then here if you observe, this is the equation for dv, and similarly if you express this one in the vector analysis as dv equal to dou v by dou x into dx, then dou v by dou y into dy plus dou v by dou z into dz. Now compare these two equations. Consider this as equation number 3 and this as equation number 4. Now if you observe in 3 and 4, LHS parts are the equations as given by dv and dv. Hence 2 can be equal. So LHS part of 3 and 4 must be same, means from RHS part of both must be same. So from those two equations, we are going to write this as minus Ex dx minus Ey dy minus Ez dz equal to, from equation number 4, that is written by here rho v by dou x into dx plus dou v by dou y into dy plus dou v by dou z into dz. Right? So now if you observe both sides here, x components minus ex dx is equal to, in the RHS part, dou v by dou x into dx. So like this, if you compare in 3 directions respectively, then those 3 can be written as minus ex dx is equal to dou v by dou x into dx. Similarly, minus ey dy equal to dou v by dou y into dy. And the third variable minus Ez dz is equal to dou v by dou z into dz. Right? So like this, if you compare both sides, dx dx, dy dy and dz dz gets cancelled. From these two relations, Ex is equal to minus dou v by dou x for the x direction, then y component as Ey equal to minus dou v by dou y, and Ez is equal to minus dou v by dou z. So from that, all the relations can be written as here Ex is equal to minus dou v by dou x, and Ey equal to minus dou v by dou y, and Ez is equal to minus dou v by dou z. Now from this, from all these components, we can write simply this equation as E equal to minus del V. So this is the relation between the E and V from point form or differential form of the equation. So if you consider integral form, means the relation as V equal to minus integral L E dot dl, and for point form that relation is given by E equal to minus del V. And we know that del V is denoted with gradient of a scalar, and we can express this one in terms of Cartesian coordinate system or rectangular coordinate system. The formula is given by here del V equal to dou V by dou x into Ax plus dou v by dou y into ay plus dou v by dou z into az. So that's why this equation E equal to minus del v is to be obtained from all the partial derivative terms and the relation integral term as v equal to minus integral L E dot dl. Right? So the relation between E and V yields us the Maxwell's equation derived for the second Maxwell's equation for the electrostatic fields, and is given by V equal to minus integral L E dot dl and E equal to minus del V. Right? So from the electric field intensity and electric potential, we have got one of the relation as V equal to minus integral L E dot dl, and the point form or differential form of that equation to be is given by E equal to minus del V. Right? So the next topic which we are going to learn is here energy density in electrostatic fields or electric fields. Energy density. So similar to that of power density, energy density or area, whatever it may be, density means it occupying some unit area, right? So unit area means we have to measure it from per meter square. And energy can be measured in joules. So joule per meter square. So energy density is can be given by here. So energy per unit area, energy per unit area, and it is given by here with a simple example. So in order to analyze this energy density in electric fields, we have considered one simple figure, an assembling of charges in infinity region to some finite shaded region. So in order to place that charges from infinity region to one particular region, we have to carry some we have to carry the charges from one place to the another place. So in order to assemble all these charges in the shaded region, so we must consider one here an example as consider 3-point charges, and those 3-point charges are denoted with Q1, Q2, Q3. Generally, point charge means we are denoted with, you have to consider the notation for that point charge as Q, and generally it is measured in coulombs. So consider the 3-point charges Q1, Q2, Q3 are placed in an empty space. Initially, this region is having empty space. So charge free region it is. So consider the 3-point charges Q1, Q2, Q3 are placed in an empty space first of all. Now no work is required to transfer Q1 from infinity to P1 because the space is initially charge free and there is no electric field. Charge free means rho V equal to 0. Charge is 0, Q is 0, and the relation between Q and V is given by Q equal to integral V rho V dV. If rho V 0 means rho V equal to, we know that the first Maxwell's equation, the relation is rho V equal to del dot D, and by default we know that D bar equal to epsilon naught into E bar. Now D0 means E is also 0. Hence, no work is required to transfer. Means initially we have to place the charge Q1 from in the particular position called P1. So no work is required to transfer Q1 from infinity to P1 because initially the space is charge free. Hence, there is no electric field. So why there is no electric field means charge free. If Q0, rho V0, if rho V0, D0, if D0 is 0, right? So that's why in order to place this charge Q1 from infinity region to P1, no work is required to transfer a charge Q1 from infinity region to the P1 because initially the shaded region is charge free region. Because of that, there won't be exist electric field, right? So work done W equal to minus Q integral A B E dot dl. By default, we know that electric potential and V and electric field intensity V is given by V equal to minus integral L E dot dl. So now we are calculating here electric potential. So from this, by default, we know that electric potential can also be defined as here work done per unit charge. Now work done firstly we have to calculate, then from that we are going to estimate how much is the energy densities exist in that particular region. So to calculate that first, according to the electric potential, here V equal to W by Q, then from that work done equal to is multiplied with electric potential is multiplied with point charge. Hence W equal to minus Q integral A to B E dot dl. Then from that, if E equal to 0, then W equal to 0. So initially, let it be work done in order to assemble the first charge Q1 at P1. Hence W1 is equal to 0. Because of that charge free region, if charge Q0 means volume charge rho V0, then rho V0 means electric flux density D0, then D0 means electric field intensity E is also 0. Then based upon that, the work done in order to assemble the charge Q1 at P1 from infinity region, then work done W1 is equal to 0. Now similarly, in order to assemble this charge Q2 from infinity to P2 and in order to assemble this charge Q3 from infinity region to P3, we must consider similar analysis as here, that is obtained as here. The work done in transferring Q2 from infinity to P2 is equal to the product of Q2 and the potential V21 at P2 due to Q1. Means in order to assemble the charge Q2 from infinity to at point P2, it is equal to the product of Q2 and the potential V21. Means it is the potential difference between 1 to 2 at P2 due to the charge Q1. So, and that V21 can be given as here. The work done in order to assemble or positioning charge Q3 at P3 is equal to the Q3 into V32 plus V31. So, in order to assemble charge Q3, then Q3 into V32 plus V31. So, from this statement, we are going to calculate W2 work done in order to assemble charge Q2, and this statement we are going to calculate the work done in order to assemble the charge Q3. So, the work done in positioning Q3 at P3 is equal to W3 equal to Q3 into V32 plus V31. So, it is the potential difference between 2 to 3 and V31 is said to be potential difference between 1 to 3. So, first of all, the total work done in positioning the 3-point charges means, so from the figure, we are going to assemble how many point charges? 3-point charges Q1, Q2, Q3 and the respective positions of P1, P2, P3. For the first charge, in order to assemble this Q1 at P1, work done is 0. And in order to assemble this charge Q2 at infinity to P2, we must consider the potential from P1 to P2. And in order to assemble this charge Q3, we have to consider the potential from P1 to P2 as well as P2 to P3. So that is given by here. The work done in transferring Q2 from infinity to P2 is equal to the product of Q2 into V21. That is given by here W2. Similarly, the work done in order to assemble the point charge Q3 at P3 is equal to the Q3 into V32 plus V31. So from 2 to 3 and from 1 to 3. So the total work done in positioning the 3-point charges, that is given by in electrostatic fields. Hence the notation is given by WE. So sum of 3 is given by work done in order to assemble charge Q1 and work done in order to assemble charge Q2 and work done in order to assemble charge Q3. Hence 3 work dones are to be added to get total work done in order to assemble 3 charges in the electrostatic fields. Hence WE equal to W1 plus W2 plus W3. Now substitute, already we have analyzed W1, W2, W3, then 3 are in this equation, means WE equal to 0 for the first case. Why? Because initially charge free region, hence W1 equal to 0. For the W2, it is multiplied with Q2 is multiplied with V21 and W3 is given by Q3 into V32 plus V31. Hence total work done in order to assemble 3-point charges is given by W1 equal to 0, W2 equal to Q2 into V21 plus Q3 into V32 plus V31. Okay, so energy WE. Now based upon this, we are going to simplify that equation. Means if you consider that will be in the order as like P1, P2, P3. Then in order to assemble 3 respective charges as Q1, Q2 and Q3, then previous equation is to be obtained. So now we want to position the charges in the reverse order, means in the descending order like P3, P2 and P1, and the charges were also be represented in reverse order, that is Q1, Q2 and Q3. Right? So P1 and P3 positions are interchanged and Q3 and Q1 positions are to be interchanged. That's why, see here, if the charges are positioned in the reverse order, means Q1, Q2, instead of positioning Q1, Q2, Q3, we are placing Q3, Q2, Q1 in the reverse order, descending order. Now, that is the case, the work done means in order to assemble the first charge from infinity to at P3. So, initially it is charge free region means W3 equal to 0. Now, from P3 to P2, now it is given by W2 equal to Q2 into V23. And for the charge Q1, in order to assemble the third charge Q1 from infinity to P1, and it is given by Q1 into V12 plus V13, right? So WE equal to 0 plus Q2 into V23 plus Q1 into V12 plus V13. So previously what that is, if your charges are in the same order and we want to locate the respective Q1, Q2, Q3 in the respective positions as P1, P2, P3, then total work done in order to assemble 3-point charges are given by 0 for the first one W1 and for the W2 Q2 into V21 plus W3 Q3 into V32 plus V31. Suppose if the positions means places are to be interchanged and charges are also placed in the reverse order. Means if the charges are positioned in the reverse order, then the work done in us due to assemble the three charges like Q3 and here it is the Q2 and here it is the Q1. Now to assemble three charges in the reverse order, we must consider here work done as W3 and this is W2 and this is W1. Hence WE equal to W3 plus W2 plus W1. Then W3 is initially 0 and W2 is Q2 into V23 plus W1 is Q1 into V12 plus V13. Now by adding those two, previously what we have the equation that is WE equal to 0 plus Q2 into V21 Q2 into V21 plus Q3 into V32 plus V31 is the previous one. Now here W equal to 0 plus Q2 V23 plus Q1 into V12 plus V13. So consider that as one equation and here it is the equation number 2. By adding 1 and 2 means if you add LHS part of 1 and 2, LHS part of these two equations will have the same, that is WE and WE. So 1 plus 1 becomes 2, hence it is 2WE equal to, now if we are adding the first one to this, then here Q1 into V12 plus V13 and previously it is from equation number 2 Q1 term is given by Q1 into V12 plus V13 and from here Q2 into V21 is the order ascending order W2 and if you are positioned in the reverse order W2 is given by Q2 into V23. Now if you are going to add those two then Q2 into V21 plus V23. Hence this can be collectively can be written as Q2 into V21 plus V23 plus. Similarly for charge 3 Q3 into V32 plus V31. So by adding 2 and 1 then 2W equal to Q1 into V12 plus V13 plus Q2 into V21 plus V23 plus Q3 into V32 plus V31. Now in short we can written as this one 2WE equal to Q1 means V12 plus V13 collectively can be written as V1 and V21 plus V23 can be written as V2 and V32 plus V31 can be written as V3. Then three positions are replaced by here 2WE equal to Q1 V1 plus Q2 V2 plus Q3 V3. Now based upon that 2WE equal to not 2WE here. So this is not there. Then from this WE equal to 1 by 2 into Q1 V1 plus Q2 V2 plus Q3 V3. So if you are having 3-point charges Q1, Q2, Q3 in order to assemble in the P1, P2, P3 or if you are positioned in the reverse order then based upon that the work done in order to assemble 3-point charges, we must calculate it as 1 by 2 into Q1 V1 plus Q2 V2 plus Q3 V3. So this is to be obtained according to the electric potential relation, that is V equal to W by Q. So electric potential can be defined as work done per unit charge. Then from that, work done can be calculated as it is the product of electric potential and the point charge. So now based upon this relation, we have got WE equal to 1 by 2 into Q1 V1 plus Q2 V2 plus Q3 V3. Right? So if you have 1-point charge, 3 particular point charges, then we have that relation. Then instead of having 3-point charges, if we have multiple number of point charges, means if we have n number of point charges, then collectively this can be written as WE equal to 1 by 2, then summation of k equal to 1 to n Qk Vk. If we expand this equation 1 by 2, we substitute k by 1 to 3 n numbers, then it can be written as Q1 V1 plus Q2 V2 plus Q3 V3 plus and so on plus Qn Vn. Okay, so in general, this work done in order to assemble 3-point charges in electric fields is given by W equal to 1 by 2 summation of k equal to 1 to n Qk into Vk is the n number of point charges case. Right? So instead of point charges, so now we have 3-point charges. If we have n number of point charges case, then we have got the equation as 1 by 2 summation of k equal to 1 to n Qk into Vk. Now instead of having a particular point charge, suppose if that particular region has a continuous charge distributions. In the electric fields, there are 3 continuous charge distributions as rho L, rho S and rho V is exist. So here rho L is said to be line charge density and it is measured in coulomb per meter, and rho S is said to be surface charge density and it is measured in coulomb per meter square, and rho V be the volume charge density and it is measured with coulomb per meter cube. So 3 continuous charge distributions in the electric fields is given by rho L, rho S, rho V. Now if we express all these continuous charge distributions in work done's case, then it can be written as, means in place of Q, we just write, as we know that the relation for point charges and the 3 continuous charge distributions as Q equal to integral L, rho L dl, and Q equal to integral S, rho S ds, and similarly for volume, Q equal to integral V, rho V dV. Right? So now if you substitute in place of all 3 Ks by respective 3 continuous charge distributions, then work done in electric fields in order to assemble line charge, for surface charge, for volume charge, then the equations are to be given by WE equal to 1 by 2 integral L rho L V dl for line charge. Rho L is to be considered as here line charge density. That's why work done in order to assemble this line charge is given by WE equal to 1 by 2 integral L rho L dl, and the charge is given by here integral L rho L into dl and that is multiplied by here V. So general formula is work done is equal to Q into V. Now Q is replaced by rho L and V is considered as here extra term. Similarly for surface, W equal to 1 by 2 integral S rho S V ds. So for surface charge means same formula, if we substitute Q by integral S rho S ds, then extra term is multiplied is here potential V. Now W equal to 1 by 2 integral V rho V V dV for volume charge. Right? So in order to derive the equation for energy density in electrostatic fields, we have to consider either of the 3 relations, either line charge density relation or surface charge density relation or volume charge density relation. So in order to identify it in the easy way, now to derive, now we know that according to the Maxwell's equation for the point form, which is derived from the Gauss law, is given by rho V equal to del dot D. That's why rho v is exist in which case? Volume charge case. That's why we have to consider the final result as We equal to integral V 1 by 2 integral V rho V dV. Right? So to get that energy density in electrostatic fields, we have considered one of the relation in the continuous charge distributions as We equal to 1 by 2 integral V rho V dV. Work done is equal to, it is the multiplication factor which is between potential and the charge. So Q is replaced by integral L V rho V dV and extra variable is here V. That's why W equal to 1 by 2 integral V rho V dV. Right? So since rho V equal to del dot D, and we know that this one is the point form or differential form of the first Maxwell's equation to be derived for the electrostatic fields, and is given by here rho v equal to del dot d bar. Now instead of in place of rho v, you just substitute here rho v by del dot d in the above equation. So that is given by here we equal to 1 by 2 integral v del dot d v dv. So substitute in place of this rho v by del dot d. Okay. Now to simplify further, we have going to use here one vector identity formula is given by del dot VA equal to, where V is the scalar potential and A be the vector potential. So VA del dot VA equal to, this can be given as A dot del V plus V into del dot A. Del V stands for gradient of a scalar and del dot A stands for gradient of a vector. Right? V is the notation for a scalar and A be the notation for the vector. Now according to the vector identity, del dot VA equal to A dot del V plus V into del dot A. Okay. Now from this here, what we have the relation del dot D into V. So it resembles that here del dot A into V be the resultant one. So for that, from this equation we have got the relation for V into del dot A. Now from this, V into del dot A equal to V into del dot VA minus A dot del V. So from this relation, we are going to derive the term for V into del dot A. Then the equation becomes del dot VA minus A dot del V. Right? So this is to be obtained from the vector identity. Right? So where V is the scalar notation and A be the vector notation. Now substitute in place of V into del dot A. So in place of A, here we have, what is that vector term? Electric flux density as D. Now substitute in place of A by D in this relation here. Now consider that equation WE 1 by 2 integral V. Now instead of in place of del dot D into V, you just write this equation. Means WE equal to 1 by 2 integral V del dot D V. Means del dot VA minus A dot del V into V dV. Right? So that equation can be written as, so and split the integration for respective two terms. Hence this can be given by 1 by 2 integral V del dot VD. Why? Because here A is there. In place of A, here we have D. Now dV minus 1 by 2 integral V D dot, means A by D dot del V into dV. From this vector identity, we just substitute in place of A by D in this case. Right? Where D is said to be electric flux density. Okay. So now by applying divergence theorem to the first term on the right hand side of the above equation. So what is there in the right hand side of that equation? 1 by 2 integral V 1 by 2 integral V del dot Vd dV minus 1 by 2 integral V d dot del V dV. So for that, if you apply divergence theorem, means as we know that divergence theorem gives the relationship between surface to volume integrals. Right? So and it is given by here closed surface integral S A dot ds is equal to integral V del dot A dV. This is the general formula for the divergence theorem for vectors, right? So by applying divergence theorem to the first term on the right hand side of the above equation. So in the previous case, we have 1 by 2 integral V del dot Vd into dV. And this can be, if you apply the divergence theorem to the RHS part of first term, means in RHS part of first term contains, this is the relation. Now if you replace volume by surface integrals, why? Because here we are applying divergence theorem and it also gives the relationship between surface to volume integrals. Hence 1 by 2 integral closed surface integral is, so del dot Vd is replaced by Vd dot ds. Why? Because Vd is a vector here and in place of A here we have Vd. That's why d dot ds can be, d means Vd dot ds. And the second term is as it is we have considered, then minus 1 by 2 integral V d dot del V into dV. Okay. Then which is equal to W equal to minus 1 by 2 integral V d dot del V dV. So we can neglect here the first term which we have considered in the previous equation. Why we have been neglected? Means as V is varies in point charges, means the formula is Q by 4 pi epsilon naught R, and electric field intensity E for a point charge is given by Q by 4 pi epsilon naught R square into AR. So if you have a single charges, means we have considered here V equal to Q by 4 pi epsilon naught into R is for the potential, and E equal to Q by 4 pi epsilon naught R square into AR is for the electric field intensity. So instead of having a single poles, if we have dipole moment, dipoles means two poles, two objects, two charges are differed by a small distance. Suppose if you have a point charge Q plus and a minus charge Q is located at this one, and the distance between these two is given by small d, means the two dipoles which are differed by a small distance as d and the magnitudes also are to be same case, we have considered the term called dipole. So for that dipoles, the Vs varies 1 by r square and Es varies with 1 by r cube, right? So if you consider here this one as V and D. So V is generally measured as with respect to r square and D as r cube. Then into surface area, means if you multiply that for surface areas, means measured in meter area meter square, and the area radius is given by here with respect to the r square. So this r square and this r gets cancelled and remaining as here 1 by r. So for normal variables it is 1 by r, and for dipoles it is varies 1 by r square. Like that, if you keep on increasing the values of denominator terms as r square, r cube and so on, then the radius is going to reduce. Hence the surface becomes very very less. Hence we can neglect this 1 by 2 integral S Vd dot ds. So minus 1 by 2 integral V d dot del V dV is left out, right? So that's why the second term which is left out is here minus 1 by 2 integral V d dot del V dV, right? So if you consider as this one, from that if you're going to give the relation, means as we know that E equal to minus del V, so the relationship between electric potential and the electric field intensity is given by E equal to minus del V. Then in the formula itself we have the negative, and in the equation we have a negative. Minus of this minus becomes positive, and if we substitute in place of del V by E, then 1 by 2 integral V d dot E dV, right? So as we know that D and E relation is D equal to epsilon naught into E and E equal to minus del V, we substitute two relations here, 1 by 2 integral V d dot E dV, or in place of D by epsilon naught into E, then 1 by 2 integral V epsilon naught into E dot E dV. Right? So this becomes 1 by 2 integral V epsilon naught E square dV. So from that we have got WE equal to 1 by 2 integral V epsilon naught E square dV. So E can be measured in volts per meter. E square means volts square per meter square, and here epsilon naught is measured as farad per meter. Hence the energy is multiplied. WE stands for here energy density in electrostatic fields, and it is measured in coulomb per meter cube. Joule per meter cube. So energy can be measured in joules, and according to this statement, it is measured in joule per meter cube, right? So WE equal to half into epsilon naught E square, which is known as electrostatic energy density. Energy per unit area is generally defined as energy density, and for electrostatic energy density is given by WE equal to 1 by 2 integral 1 by 2 epsilon naught E square. Like the energy stored in the capacitor is given by half CV square, right? So C is the capacitance and V be the potential difference between the two plates. So this is the way we have derived the equation for electric energy density in electrostatic fields. So from this we have got two relations as WE equal to 1 by 2 integral V d dot E dV, or WE equal to 1 by 2 integral V epsilon naught E square into dV. Right? Energy density in electrostatic fields means we have to derive the equation as 1 by 2 integral V epsilon naught E square into dV, and it is measured in joule per meter cube. Okay? So this is the way we have derived the energy density in electrostatic fields. So in this lecture, we have discussed two topics. One is the relationship between electric field intensity E and the electric potential as V, and it is given by for the integral form as integral L V equal to minus integral L E dot dl, and the point form as E equal to minus del V. So, and next topic we have discussed is energy density in electrostatic fields, and from that we have got the relation as WE equal to 1 by 2 integral V d dot E dV, or WE equal to 1 by 2 integral V epsilon naught E square dV. Okay, so in this lecture we have learned two topics. Firstly, we have revised what do you mean by the electric potential, how many relations we have got. Then from that, electric field intensity and electric potential, how those two are to be differed. Then that we have discussed, and the next topic we have discussed is energy density in electrostatic fields. So in order to find the energy density in electrostatic fields, first of all, we must know how much is the energy is required, or how much is the work done in order to assemble the charges from the infinity space to the from particular space. So initially we have considered one first case as initially that shaded region has free of charge region, hence that charge q equal to 0. If charge q 0 means volume charge rho v 0, then rho v 0 means flux density d 0, then from that E 0. Based upon all these assumptions, we have got the three equations: work done in order to assemble first charge q1, and work done in order to assemble second charge q2, and work done in order to assemble charge q3. Then based upon that, we have added WE equal to W1 plus 2 plus 3. Now we are positioned the 3-point charges Q3, Q2, Q1, or Q1, Q2, Q3 in the reverse order case, then Q3, Q2, Q1. Then this is the case. Positions are also to be interchanged P3, P2, P1 in order to assemble These three charges we have considered again in the reverse order case as W3 as first one, W2 as the second one, and W1 as the third case. This is the way we have analyzed. Finally, we are added. Then energy density in electrostatic fields can be obtained as WE equal to 1 by 2 integral V d dot E dV, or in general can consider it as WE equal to 1 by 2 integral V epsilon naught E square dV as the electrostatic energy density, and it is measured in joules per meter cube. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.